So in this situation, our first question, we have a cube that's 20 centimeters per length side. So that means that we've got one that is 20 centimeters by 20 centimeters by 20 centimeters deep. So 20 by 20 by 20. Now, it says on here that it is actually only 2 centimeters submerged. So that means our water line only goes up 2 centimeters on our cube. So our volume is not going to be the total volume of the cube, but only the volume that is actually being submerged. So I'm going to start off by summing the forces of my cube, and it's floating there, so my sum of the forces is going to be equal to 0. That's going to be equal to my buoyancy force minus my force of gravity, mainly because my gravitational force is pulling it down. I'm after the mass, so I'm going to solve for Fg. Fg is then going to be equal to my force due to buoyancy. Expanding those out, I get that mg is going to be equal to rho vg, just using the formulas that we've used. Gravity is the same on both sides in this situation, so we're going to look at cancelling them out. That means our mass is then going to be equal to rho times by v. So this is the volume of the object that is displacing the fluid, as well as the density of the fluid. We can plug that in, so we get our 1,000, because that is the density of our fluid, times by the volume. So that's going to be 0.2 times 0.2 times 0.02. This is going to be the volume of it being displaced. It's not the full 20 centimeters, but this is the volume of displacing the fluid, which comes out as being 0.80 kilograms, our expected answer. In our second one, a hollow containered cube has sides of 20 centimeters. So it's roughly the same question, and it sits there with 2 centimeters submerged. So exactly the same situation as before. What we need to do is calculate the mass needed to be added to sink the cube. So to sink the cube, the entire thing must be underwater. So that means that instead of having just 2 centimeters submerged, we need the full 20 centimeters submerged. So the minimum amount is when it's not going to accelerate down, it's not going to be pushed up. We are going to still need our forces to be equal to 0. So we're going to sum the forces in the y to be equal to 0, which is then going to be equal to exactly the same that I had before, our force of buoyancy minus our force of gravity. We're again going to solve for our mass. So Fg is equal to Fb. Our mg is equal to rho vg. Gravity being the same for both of these situations, so our mass is then going to be equal to rho v. Now we know that the entire cube is going to be submerged. We can say that our rho, our density, so 1,000, times by the entire volume of the cube. So 0.2 times 0.2 times 0.2. And this is going to be equal to 8. The key word here is the mass added. So in this situation, in our first question, we actually calculated the mass of the cube in the first place. So if this was an independent question, you would need to calculate the mass of the cube first before you can remove it from there. Otherwise, you could try and put it all into one calculation. But we're going to say that the mass added is going to be equal to the total mass minus the mass of the container, which is equal to 8 minus the 0.8, which is then going to get me the 7.2 kilograms. In the final question, we're looking at a buoy of area 0.2 meters squared, and it's floating with only 0.75 meters of it submerged. So let's treat this in the most simplest form as a cylinder. So I'm just going to draw a cylinder down here. two sides, its area down the bottom is going to be 0.2 meters squared. It's going to go into the water 0.75 meters. And that's where my water line is going to be. Exactly the same as my other calculations, it's saying that it's floating. So the sum of my forces in this situation, the sum of my forces in the y is going to be equal to 0, which is going to be equal to my force of buoyancy minus my force due to gravity. Force of gravity is equal to our force of buoyancy. mg is equal to rho vg. Therefore, again, I get my m is equal to rho v. I now have an area, so the area at the bottom of my buoy versus the height at which it is submerged. So I get my density, 1,000, times by the 0.2 times by the height, 0.75, which should come out to being 150.